Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about binary search trees. So let's first define what a binary search tree is, because it's surprisingly a little bit confusing. A binary search tree is a binary tree, and it's a tree that you can perform binary search on. So since it's a binary tree, each node can have at most 2 children, where it has a left and right pointer to those children. And you can perform binary search, which means the nodes are ordered, and you know at any node if you need to go left or right. So a binary search tree is a binary tree like any other binary tree. Each node is going to have a left and a right pointer to its children. And a binary search tree means you can perform binary search. So any given node is a midpoint, which is equivalent to when we perform binary search on an array, we find the midpoint, and since the array is sorted, we know all the items to the left of the midpoint are smaller, and all the items to the right of the midpoint are larger. So in a binary search tree, we can perform binary search because any given node is similar to a midpoint. And for a tree to be a binary search tree, it must be completely ordered so that all the items to the left of a node are all smaller and all the items to the right are all larger. So just as if it was an array. Each node is considered a midpoint, and left is smaller and right is larger. So when we say binary search tree, another definition for it is saying it's equivalent to a sorted binary tree. So all the nodes in the tree are ordered. And the ordering is exactly like a sorted array, where any node or any item, all the items in the left subtree are going to be smaller, and all the items in the right subtree are going to be larger. So let's visualize exactly what this means. Let's take this binary search tree. We see it's a binary tree because all nodes have at most 2 children, and we'll also see that it's sorted. So if we start at the root node, we see that its value is 50. This must mean all the items in its left subtree are smaller than 50, which we see here, and all the items in its right subtree must be larger than 50. So let's just highlight those where all the orange nodes are smaller than a current node and all the blue nodes are larger. So then what if we go left? Well, a binary search tree means all the nodes to the left are smaller than the current node and all the nodes to the right are larger. So we see for a value of 40, again, anything to the left is smaller and anything to the right is larger. If we instead went right from the root node, we have the value 55. It doesn't have a left subtree, so we don't have to consider any values being smaller to its left, but it does have values to its right. And we see all the values to the right of this are larger than 55. So the benefit of a binary search tree is that the operations happen in O of log n time, just like binary search. If you're searching for a node in a tree, let's say 42, you can perform the process of binary search. So we start at 50, we know 42 is less than 50, so we must go left. Then we reach 40, we know 42 is larger than 40, so it must be in the right subtree of this node, so we move right. Then we reach 45, we know 42 must be smaller than 45, so it must be in its left subtree. Then finally, we reach the number 42. So even though we have 10 nodes in this tree, we removed approximately half each time when we made a move, and it only took 3 operations. 1, 2, 3. And then we found the node we were looking for. So this is why we get log n time. We're dividing the input in half each move that we make, just like as if we were performing binary search on an array. but a key constraint of binary search is that the tree must be balanced. So there must be approximately the same numbers to the left and right of any given node in its subtrees. If not, binary search trees will degrade to O of n time because it still must traverse approximately all n nodes. So let's see an example of that now. So we start at the root node 12, and in this example, if we're looking for the number 96, we touch all the nodes but 2, so we're not getting this log n time because we still need to touch nearly all the nodes. So every time we make a move, we're not eliminating half of the nodes each time because it's not balanced. So in the last example, we had 8 nodes, and we had to touch 6 of them to find the one that we were looking for. But now let's see what happens when we traverse a balanced binary search tree. So in this case, we're looking for the number 79. We started at the root node 56, and then we only had to touch 1, 2, 3, 4, 5 nodes, but we had many, many more than that in this tree. But because it's balanced, we eliminated approximately half each time, so this required many fewer operations relative to the input size. In fact, it has many more nodes than the unbalanced tree and still required less operations overall. So for a binary search tree to get log n time, it must be balanced. So on the left, we have an unbalanced tree, and we see we just must traverse all n nodes in the worst case. But with a balanced binary search tree, when you traverse, you cut out approximately half of the remaining items each move that you make. So if we start at the root and we go left, well, we cut out 5 items from the right subtree because they're no longer considered. We only consider this node and its children. Then if we went left again, we cut out 3 additional nodes, or over half of the remaining nodes because it's balanced. So every move we make, if the binary search tree is approximately balanced, we get that log n time. So the pros for a binary search tree is that it gets those fast log n operations for all operations. Because we traverse a tree to do all these operations, they're all going to take log n time. So if we want to find a node, we can find it in log n time because we're using that sorted order to go right and left and eliminate half the nodes when we're looking for an item. To insert a node, you traverse down the tree and look for the spot it must go relative to the order of the whole tree. So if the item you want to insert is larger than a given node, you're going to go right. Or if it's smaller than the current node, then you go left. And eventually, when you reach a leaf node, then you insert it to the right or the left of this node. So we can insert in log n time. Then it's the same for search and delete. You simply use the ordering of the tree to find the node that you want, and because you're eliminating half the nodes with each move you make in the traversal, these are also going to be log n time. So this ordering not only enables us to get this log n time, but it just gives us a relative understanding of where items can be located in a tree, which can be useful in interview questions. And finally, binary search trees have a flexible size, just like all other trees. So we can have as many nodes as we want in the tree, and to insert them, we just append it as a child to the correct node in the tree. So we just use that left or right pointer and attach a child as a reference. So this makes binary search trees a very loose and flexible data structure. The con of binary search trees is that they must stay balanced. The only way we get this log n time is if it's a balanced binary search tree. If it's not balanced, then in the worst case, we're still going to have to traverse all n nodes. So the final question is, will binary search trees always be balanced in interviews? Typically, the answer is yes, but you need to make sure this is true. So you can either ask the interviewer if it's balanced if the prompt doesn't specify, or you can just tell them you're assuming it's balanced. And in real-life scenarios, when we're using binary search trees, we usually use an implementation that is self-balancing. And the two most popular implementations are AVL trees and red-black trees. So in an interview, you could say something like, I'm assuming it's a self-balancing tree like an AVL tree or red-black tree, and that's most likely sufficient. It's very unlikely you're going to need to implement balancing or implement one of these AVL or red-black trees, but it's good to know these common names for what people use in real applications. So after this slide, we're going to quickly visualize what AVL trees and red-black trees are, but for interviews, most likely all you need to say is that AVL trees and red-black trees will enforce the tree to always be balanced. So if we go back, if we used an AVL tree or a red-black tree, we would never get an unbalanced tree. It would never look like this left tree at all, because they self-balance. So if you insert or remove an item, it's going to perform operations to maintain balance, so you're always going to get those login operations. So let's visualize AVL trees and red-black trees. It's very rare that you're going to actually need to use these in an interview, so even what we'll learn here is outside of the scope, but it's more for just your knowledge. What's really important is that AVL trees and red-black trees self-balance, so they stay balanced and get those login times. So let's first look at an example of an AVL tree on visualgo.net. And what an AVL tree does is looks at the heights of two child nodes for any subtree and ensures these heights differ by no more than 1. If they do differ by more than 1, then it rebalances the tree. So we can see here that once the tree got out of balance, it recognized this and then rebalanced the entire tree to maintain these login operations. For a red-black tree, it maintains if a node is red or black by storing an extra bit within that node, and then it will rebalance the tree if any of its parameters are off. So the red-black tree uses its encoding of red and black nodes in order to maintain balance. Thanks everyone, and I'll see you in the next lesson.